Galaxies crash and flare, yet billion light-year maps barely change. Here is the immediate takeaway: large scales wash out local chaos. The universe stays predictable when you average enough matter together. Gravity, expansion, and early smoothing set the rules we can trust. You will see patterns that survive messy details in small places. Think of tides on a stormy sea, steady under choppy waves. The big picture holds because randomness cancels in huge numbers. Gravity then locks averages into structures that hardly drift. Early inflation ironed the fabric, so wrinkles stay gentle today. Distances stretch uniformly, giving clocks the same cosmic beat. So despite fireworks nearby, the background story runs surprisingly straight. Picture a crowded galaxy cluster, buzzing with orbits that look chaotic. The cluster still settles into balance, called virialization in plain words. That word means kinetic energy balances the pull of gravity. This matters for predictability because the whole stays stable over time. Stars and galaxies zip around, yet the center barely budges. Random directions cancel, while gravity corrals motion into a steady envelope. The hot gas heats to a temperature that matches the cluster mass. Speeds land near a predictable spread, like traffic on a ring road. Coma cluster shows this clearly, with speeds near 1,000 kilometers per second. Its gas glows near 90 million Kelvin, matching the expected depth. Try a quick check, double the mass and speeds rise predictably. We can estimate mass from temperature with tight scatter across systems. Bottom line, gravity averages the chaos, and balance keeps clusters reliable. There is a mind-bending claim: the universe looks alike in every direction. Cosmologists call that homogeneity and isotropy over very large scales. It means the average density is the same wherever you stand. You should care because this symmetry lets equations describe everything cleanly. Without it, predictions would depend on a special spot in space. How does this hold when structures clearly clump into filaments and voids? The trick is scale, where big enough volumes iron out local lumps. Filaments weave a web, but the web repeats again and again. Surveys count galaxies in cubes hundreds of megaparsecs across, then compare. Differences shrink to a few percent once boxes get that large. The microwave background is even smoother, at 1 part in 100,000. One sentence recap: big boxes look the same, so cosmology stays solvable. Roll back to the first sliver of a second after the beginning. Space itself inflated extremely fast, stretching tiny quantum jitters to cosmic size. Inflation means rapid expansion that smooths curvature and spreads small fluctuations. You should care because those seeds became galaxies and also kept order. Here is how it works: rapid stretching dilutes relic messes instantly. Neighboring regions lose contact, so only gentle gradients survive the rush. The initial bumps follow a near-scale invariant spectrum with simple statistics. That mouthful means similar power per octave, like pinkish cosmic noise. Planck maps confirm this shape, with a spectral tilt near 0.96. The pattern fixes starting conditions, so later growth follows clear tracks. Example in real terms: predict the wiggle size seen across sky patches. We match the measurement within a few percent across many angles. So the picture is: inflation baked predictability into the universe's blueprint. Switch to the dark skeleton, the hidden scaffold that guides galaxies. Dark matter behaves like a cold, invisible fluid that only gravitates. That short line defines it well: collisionless and slow compared to light. You should care because this scaffold decides where galaxies can live. Small overdensities collapse first, then merge upward into larger halos over time. Simulations show halos with universal shapes, regardless of their mass. Orbits mix while gravity deepens wells that look strikingly self-similar. The result is a family of profiles that repeat across scales. Take the Milky Way, with a halo mass near 1 trillion suns. Its circular speed stays flat near 200 kilometers per second. Satellite galaxies trace the same well, even after messy tidal stripping. Rule of thumb: mass follows the invisible halo more than bright starlight. Net result: dark matter's scaffold anchors structure, so predictions keep working. Now draw a cosmic ripple, a faint ring around every massive region. That ring is the baryon acoustic oscillation, a perfect standard ruler. It means early sound waves imprinted a preferred separation between galaxies. You should care because that fixed scale lets us measure distances. Before atoms formed, photons and gas moved together like a spring. Pressure pushed outward, while gravity tried to pull matter back inward. The tug-of-war made waves that froze when atoms emerged. Today, that wavefront shows up as a slight bump in pair counts. The distance is about 150 megaparsecs as a clean landmark. Surveys like BOSS and EBOSS see the bump again and again. Measure the bump's angle, then you get the cosmic yardstick today. Tiny test, shift the bump, and models fail across many datasets. Bottom line, the frozen sound horizon keeps maps aligned across time. Zoom out to the entire stage, where geometry steers the flow. General relativity reduces the stage to simple expansion rules on average. The Friedmann equations link matter, curvature, and dark energy to the expansion rate. That sentence defines the engine. One number h controls the growth. You should care because this engine predicts sizes, ages, and growth speeds. Put in the average densities and it outputs a time history. Matter slows expansion, while dark energy accelerates it late on. Growth of structure then follows the background, rising in lockstep with H. Observations favor a mix around 30% matter and 70% dark energy. The present H sits near 70 kilometers per second per megaparsec. Feed those into models and you forecast cluster counts by redshift. Sci-fi note, swap parameters slightly and predictions drift far from data. What to remember: simple expansion rules tame the universe at scale. Think about tossing many dice, where totals get surprisingly stable quickly. That same logic saves cosmology through averaging and coarse graining. Coarse graining means we blur small details to track big behavior. It matters because predictions need stability, not whiplash from tiny features. Here is the working idea: random errors cancel like coin flips, double the number of regions, and typical deviations drop by half. Galaxies become tracers and their shot noise fades in huge volumes. Velocity tangles wash out, leaving smooth flow that follows expansion gradients. Example in real terms: count galaxies inside a 300 megaparsec box. The fractional fluctuation falls near 1%, barely nudging global numbers. Peculiar motions also shrink, from thousands to a few hundred kilometers per second. One sentence recap: enough samples turn noise into a quiet background. Shift to a bright galactic core, where a black hole launches jets. Feedback is the cycle where energy from stars or black holes pushes back. That plain line means galaxies regulate themselves, instead of runaway extremes. You should care because regulation pins galaxies to tight scaling relations. Supernovae stir gas and drive winds that slow fresh star birth. Black hole jets heat halos, preventing catastrophic cooling in massive systems. Together they shape gas supply and steer galaxies toward predictable tracks. The jet power can reach between 10 to the 37 and 10 to the 39 watts. Clusters show giant cavities, matching the energy needed to offset cooling. Spiral galaxies settle onto Tully-Fisher slopes with small scatter. Ellipticals tie black hole mass to bulge dispersion with remarkable regularity. Rule of thumb: feedback clips the highs and lifts the lows gently. Bottom line: self-regulation narrows outcomes, so forecasts stay trustworthy. We started with a contradiction: chaos nearby and order at scale. The payoff is simple: averaging plus gravity keeps the big map steady. Inflation prepared smooth starting lines, and expansion synced the beats everywhere. Dark matter supplied scaffolding, while acoustic ripples locked a standard ruler. Simple equations then drove growth, and coarse graining canceled leftover noise. Feedback guarded against extremes, keeping galaxies near stable tracks. So a choppy sea still carries a steady tide underneath. If this big picture clicked, consider sharing the video with a friend. One thoughtful share grows this curious corner of the internet. Thanks for watching and for caring about the universe's calm order.